Hello again, welcome back to my series. This time we'll talk about NLP, specifically about reading GPT-2 source code. Basically, we will look at this small example of a text prompt given. This is the famous one about unicorns. We'll tokenize it, we'll apply the model and generate some new text coming out of this model. And then we'll read the code of how that actually happens. So we will just go through that in the debugger. We'll see how tokens are fed into the transformer, how all of that happens, how causal attention masking is happening, and so on. And then later on, we'll actually look at the sample training code. Obviously, it's probably not the training code that was used to train the model. Unfortunately, that's basically the secret of OpenAI, and companies tend to be secretive about this nowadays. But it's a sample of how that might look like, which hopefully will help you get more understanding about what that model actually does. Here is the plan for today. So we'll start with some prerequisites. So what you actually need to follow along. I plan to make it into a series, and this is like an introduction to the series, and I want to talk a little bit about my learning principles. Then describe a little bit of history of what was before that, before GPT-2, of what was after, to help you understand the context of what is going on. Then we'll go through the transformers taxonomy, about GPT-based models, about BERT-based models, and about T5. Then we'll actually talk about GPT-2, what is causal language modeling, what all of that is about. Then we'll read the inference code for GPT-2, specifically the version in PyTorch by HuggingFace. And then we'll also read through the example of fine-tuning code for GPT-2. So this is going to be a video for advanced learners, so I'm not going to explain what is a transformer. I assume that you know some stuff about deep learning, but I do not assume that you know anything at all about text. So it's ideal if you are actually a machine learning engineer or if you know something about deep learning, but then I will actually go from the very beginning about actual NLP and then hopefully explain all the modern concepts. And as I said before, I want to make it into a series, and I have some idea about how the series will look like. So this is a work in progress. Today we're talking about GPT, and I consider this to be the first big transformer-based model working with text, meaning that it's also quite simple in terms of how many concepts are actually used in the model. Then we'll talk about BERTs, the bidirectional transformers that might be useful in some cases, might solve some problems better. And after the first BERT by Google, we had a lot of variants like Roberta, Diberta, and all of that. And there's really a lot of them, and they keep coming out every year. But again, BERT is the first and the simplest one. Then we'll talk about T5, the different model from Microsoft that actually uses encoder and decoder at the same time. Then we'll talk about stuff that maybe takes it all in a little bit different direction. So for example, E5 is basically saying that, okay, we have the model that is able to answer questions. It's good enough in text understanding. But if we want to search through the entire internet or through a huge database, we cannot just put all of that into the model's context. So instead, we want to have effective search, and for that, we want the representation of text, the embedded representation, to be such that we can actually search through that effectively, and E5 solves the problem. Then we'll talk about some advanced GPTs. So obviously, GPT-2 is a language model, so it is good at talking, it's good at generating text, but it's not really that useful. If you ask it how to solve a problem, it'll just treat it as a prompt and just continue describing the problem. As we'll see later, we can actually play around with that. So InstructGPT and later ChatGPT introduced new techniques to basically fine-tune the model, to actually tell it to be useful, to solve your problem, fine-tune it using reinforcement learning, RLHF, and all of that. And I'm hoping to get to there as well, and a lot more to come. And my learning principles are, first of all, I don't want to just make isolated videos about specific models. And so then if it's an advanced model, you can't really understand it because there's so many of new concepts there. I want it to be more of a learning path. So you start somewhere and then you move towards the goal, towards state of the art, towards the model that you need, and you make it step by step. And that way it's much easier to learn. New concepts are introduced gradually. So it's basically about learning it all, not just one specific model. I want to tell content in an up-to-date manner, which is, I suppose, really useful compared to some courses you might find on Coursera or elsewhere. So I'm not going to talk about word2vec. I'm not going to talk about recurrent neural networks, bag of words, all of that. We will just start with transformers because, well, it's 2024 now. We know that they work. We know that that's how we should start with NLP at least. And then maybe we'll look at other concepts because they might be useful after all in some advanced techniques, but that's not for the beginners, certainly. And finally, I want to be really technical. So we are going to be reading a lot of code. And I also want to keep in touch with the world, meaning that the code I want to read is not just some code that is maybe a sample code that explains some concept. I strive to make that as real as possible. Ideally, the actual reproducible models, when you can be sure that this is the exact code version that was used to create a certain product or achieve a certain benchmark. And that way, a lot of new details actually come to light, because in sample code, in tutorials, a lot of stuff typically gets skipped because it's ugly, it's not really interesting. And then you realize that even though you sort of know everything, when you start training, maybe in your real project, it just doesn't work. Because turns out that all those ugly details were actually needed to make that work. And so it's important to know that. Unfortunately, that's not always possible. So in some cases, it's actually quite possible. Like my favorite computer vision, models like YOLO, Data, ResNet, all of them are open source. All of them are trained completely on public data sets. All of them have up-to-date implementations. So you can just download the dataset, download the source code. It's readable, it's in PyTorch, it's up to date. So it's quite easy to understand what's going on in there. And then you can run it on your own computer. And with modern GPUs, it takes now much faster than it was 10 years ago. But that's not always the case. So sometimes, and in case of giant language models, that's quite often, the dataset is so big, and even the model might be so big that it's just unrealistic to play with it yourself on your own computer or pre-train it at least. Sometimes the training code is public, but it is outdated, like in BERT, it's written in TensorFlow 1. So I can't really read that, to be honest. So it makes it more complex. Sometimes the code itself of the model, the inference code and the weights are public, but then the dataset is not public and the training code is not public. And this is the case for GPT-2, for example, or for Stable Diffusion. So we know what the model is, we can download it, we can use it on our own computers, but then we're not really sure how exactly they got to that model, how did they achieve it. Like, how did they transform the data? I guess we do know all the major details, but then a lot of implementation is hidden. So that's not ideal, but we'll have to work with that. Sometimes neither code nor weights nor data sets are public, like in case of ChatGPT. And then we can basically get some information from presentations, from papers, and then try to assemble it into some sort of coherent picture. And my learning, my course is going to be partly about understanding such details and learning where to find information and how to judge if information is good or not. Okay, now a little bit of history. So again, prehistoric era, deep semantic structured models, word2vec, recurrent neural networks. We're not going to talk about that today. For me, I would say that it all started in 2017 with a paper called Attention is All You Need. It is often called the most influential paper of the decade, at least. You can see it, at least by how much it is cited. So it's more than 100,000 citations on Google Scholar. That's definitely like at least 10 times more than I've seen with any other paper about machine learning. And then if you go to the actual paper, because this is the paper, attention is all you need. This is the paper that basically introduced the architecture for transformers. Then if you actually see what they use it for, it's all quite niche specific to machine translation. So the model is trained on this English-German data set. They measure some metrics on translation. And that's basically what they did in the paper. So that they got this amazing tool, but only actually tested it out on this one niche task. Then a year later, GPT-1 comes out, and GPT stands for Generative PreTraining. And so this is the paper about generative pre-training. And basically what they do now is they say that, okay, we have this amazing architecture called transformer, and it is good at working with text. And then we'll do what we call generative pre-training or causal language modeling. That's when we basically try to predict next token. We just follow through the text. We're not really doing supervised training because we don't really need labels. We just need unlabeled text. And then we show it some portion and then tell it to predict the next token or next word. And we train it to do that well. And what they found out in this paper is that by doing so, by pre-training on this large corpus of unlabeled data, they were able to beat a lot of these niche specific tasks and basically improve current state of the art. To me, it sort of sounds as if some dude just appears at a marathon where there are athletes who trained for the past decade and improve techniques and have the special gear, and then this guy comes in with flip-flops and like this is the first time you've actually heard about the marathon, and then he just runs and beats everyone by like 20 minutes. And then the next day he goes ahead and beats the chess competition and then the singing competition. That's pretty much how it looked like. So in all of these, like they tell that they won in 9 out of 12 tasks. These tasks are basically branches of science where a lot of people actually try to improve the accuracy using specialized techniques, learning a lot, labeling the data, playing with the architecture to make it more specific to this task. And then this one generic transformer comes along, it pre-trains on this large text of data and then just beats it all. And thus also proving that you can do that by just generative pre-training. So look at machine translation, for example. You needed to have like the huge data set with translation pairs where you have like a piece of text in one language and translate it into another language. And that is quite hard to get. You usually need to label it manually, or you need to really look quite hard to find something like that. So it's not readily available. And then GPT just tells you that, just train on the entire internet. And in there's just so much stuff that you learn translation as just a byproduct. And then you can query the model and it will answer you in French, in German, in Chinese, and whatever. But that's GPT-1. It's much smaller than GPT-2 that we're going to talk about today, much smaller than ChatGPT. So it's not really, it's good. It's able to handle text quite well, but it's not yet perfect. Then a year later, OpenAI releases GPT-2. So it's not really different in terms of architecture. It's just a scale up, more parameters, more data. And the reason we look at that one first is because they actually released the code for it and the weights. The code, again, is in TensorFlow, but then it was re-implemented into PyTorch by HuggingFace, and HuggingFace libraries are used pretty much everywhere at the moment, so you can be sure that the implementation is good enough. Then in 2022, InstructGPT came out. Again, apart from scaling it up, they also introduced new techniques like fine-tuning, reinforcement learning, LLHF to actually turn this talking head that just generates text into something useful. Then ChatGPT came out that actually proved that it's useful, and a lot of people started using that. In parallel, in 2018, BERT came out, which basically said that, okay, we can use transformers not just for text generation, but for predicting something else. And by doing that, we can basically use more information from the text than some niche stuff like E5 that is used for retrieval augmented generation and so on. Now let's talk about text transformers taxonomy. All models based on transformers working with text can be broadly divided into 3 categories. So the first one, so-called decoder only, and example of that is exactly GPT. And they basically work like this. So we start with a piece of text, we tokenize it, turning that into a list of tokens or words, and then each of them gets looked up in an embedding table. So we basically convert every token to an embedding vector. And then this sequence is passed through the decoder with self-attention. And this self-attention has what is called causal attention mask, which basically means that the word in a sentence is only allowed to attend to words before that. So the word in, its first word, it's only attending to itself. Then the second word, a, is going to attend to itself and the previous word. Then shocking can attend to itself, the word before that, the word before that, and so on. So last word can actually see everything. And we do this, it's a restriction. So we basically zero out half of the matrix of allowed attentions. We do that as a restriction because that's how generation works. So when we start typing this sentence, when we just first start, we have to generate the word in, and we have no information when generating that word. Then when we generate second word, we know what came before that, but not what came after, because that is not generated yet. So having this restriction in the attention mask basically allows us to train the model for text generation. So the output of the decoder is the sequence of the same shape. And when we do the actual generation, we just take the last element of the sequence, which will basically respond to the next token generated. So one thing to notice here is that we basically converted this interesting problem of generating text, which might be of arbitrary length, to a classification problem. So now when we output something, basically we are only interested in this last token. And the output of the model is basically this vector of probabilities for every available token. And so tokenizers typically have something like 50,000 different tokens. And so the output of this entire GPT is this sequence, last element of which is going to just predict probabilities for the next token you have to generate. So when we actually do the generation, we take this last token, we take the probability we take the one with the maximum probability, and then just add it to our text. And that's how generation works. Second type of transformer-based models is bidirectional, like BERT. So they basically lift this restriction. So they also do tokenization, they also do self-mention, but then they have so-called bidirectional attention mask, which now allows every word in a sentence to attend to everything else. And this is less restrictive. This allows the model to see more of the context and train better. But now we cannot use it for text generation. So it's not a generative model. It is still useful. So we can, for example, train it to predict sentiment of the text, or maybe use it for search and predict how relevant this text is to this search query, and so on. So now this is closer to our old school models, which were used for regression, for classification, basically for outputting the actual number instead of just text. It is a different interface, I would say. So one thing is to just ask the model like if it's a good review or bad review. And another thing is to fine-tune your model to output a number from 0 to 1, telling the probability of good review or bad review. But BERT models basically correspond to completely different tasks being solved. Finally, another interesting model like T5 from Microsoft basically tries to do both. And this is like saying, let's say you are a writer that is writing something. So you have written a piece of content and you are about to write the next word. So now you can look at this piece of content and basically go through that back and forth and reread what you have already written. But then when you write a new word, you don't know what comes next. And so the T5 model will have the encoder with full bidirectional attention. But then the output of that will be passed to the decoder with the causal attention mask. So it's an interesting mix of both techniques. Now let's talk about the actual algorithm of GPT-2 and the causal language modeling. So first of all, tokenization. So I like to think about neural networks as something that can turn fixed length vector of numbers into another fixed length vector of numbers. So if you have managed to turn your task into that, you know how to solve it. So then how do we turn text into that? Text is not numbers. Text is not fixed length. So first we do tokenization. So we basically split the text into a certain set of tokens. And we'll look at an example that actually comes from OpenAI release of GPT-2 about unicorns. And so we can start with just letter-wise tokenization. So we split the text into letters, and that works. And it might actually be good because the vocabulary size is quite small, but then it's ineffective. So first of all, it is ineffective because transformer full self-attention time complexity is quadratic to sequence length. So you have sequence that is 5 times larger, you'd have 25 times the complexity. And like if you use ChatGPT, you also pay for tokens. So if you have more tokens, you pay more. That's one problem. Another problem is that the information contained in just one letter is much smaller than the information contained in a word. So if you look at the word shocking, for example, it's a fairly self-contained word. You understand what it means. Then if you were to just train the model to learn the same from just letters, you'd basically start with just individual letters that individually don't mean anything. Then in self-attention, one layer is able to do pairwise communications. So you basically do connection like, oh, I have S in here, I have H in there. And then after a few layers, you'll finally look at the whole word. So it basically will take some time to get to the words even, and then a few more layers to connection between words and so on. So it's less effective. Finally, it works well for English, but then what would you do with Chinese, for example? I think in Chinese alphabet, there are something like 50,000 different characters. So not ideal. Another extreme is word-wise tokenization. So when you actually just split by words, it's more effective with respect to sequence length. The vocab size is huge, so it's much more than with the case of letters. So I think in just English, we have things like few 100,000 words. And then if you add other languages, typos and so on, it will be even more. One potential problem with that is that each word is unique and is represented by its own embedding, not really connected to each other. But you might actually have words that are similar. So for example, token, the noun, and tokenization, the verb. They are similar. Basically, they have the same root. But if you just tokenize by words, you would map them to completely different embeddings, not really connected to each other. And so the model will have to learn that these two are actually connected. So it will be good to have some sort of understanding that there's a root of token, and then this generic suffix that turns the noun into a verb. Another potential problem here is typos. So if you type scientist instead of scientist, it will be a completely different word. And if it's a rare typo, the model might not be aware of that, or if it's a frequent typo, it'll just not get connected to the initial word. Then you'd obviously have rare words, and in our case, with internet, with search, you'd often see words like RTX 4090, so names of computer components, names of models, names of games, movies, and so on. And they keep coming out every year, unlike the actual proper Oxford English words that are more or less static. The number of actual words used in the language keeps changing and keeps adding new words year by year and day by day. So you'd have to do something with that. And a typical solution with models that use word-wise tokenization is to just have unknown token. So you say that, for example, you see these words and you know them. So in a shocking finding, and then you have a comma, and then you have a typo here, for example. So it will just be replaced by unknown. So the model still can infer what is happening here, but then it will have a lot of these unknown tokens, and some information will be lost. There are quite a few problems in tokenization, and different models handle them differently. So one of that is how to deal with spaces. So again, if we come back to this word-wise tokenization, we just assume that we are going to split everything by punctuation or by space. But then if we want to generate Python code, for example, we need to know where spaces are. So we cannot just ignore all the spaces. We need to know that the space is a token as well, basically. We might have a lot of languages, and we know that ChatGPT deals with all of them quite well. So you can ask it to translate something from Telugu, from Chinese, from anything you like. And a lot of languages use their own writing system, and so the model has to be aware about all the writing systems in the world simultaneously. As I said before, rare words, typos, the model needs to know about that. Another interesting problem is big and small letters. So in English, we try to start every sentence with a big word, but then the word big in the beginning of the sentence is actually the same as somewhere in the middle of the sentence. So you might want to just ignore that, and that will save you roughly half of your vocabulary size. But then you'd lose some information too. So basically, you would be unable to regenerate code, because in code you typically have class names that start with a big letter and then variable names that start with a small letter, for example. And the model needs to be able to differentiate that. And you might miss some hints from the text. So, for example, if something that looks like a noun is written with a big letter in the middle of the sentence, maybe it's someone's name. And again, this is useful information. So different models do this differently. Some models go to the more minimalistic approach. They just say that we are working with English. We are interested in this specific text benchmark like glue that tends to have like proper English without typos. And so they just ignore big and small letters. Some models like ChatGPT do work well with big and small letters, and so they have to explicitly state that in the tokenizer. So the tokenization technique used in GPT, as well as in a lot of other models, is BPE, or byte pair encoding. So the idea is that you basically start with a small vocabulary size, something like 256 unique ASCII values of potential byte, basically. And then you train on data by just counting the number of occurrences of different tokens that you have right now. And then you just unite most frequent token combinations. So you see that letter R often follows the letter T. So you unite that into the token TR, and you repeat the process. So on some step, you might have a token TR and a token AIN, and then you unite them once again to get train. So eventually, this thing gets at words. It might even get at big rhymes, like frequent words that come together. At the same time, since we've started with raw byte values, and we didn't really throw away anything, we just united tokens, this means that this tokenization is still able to represent anything. And we stop when a certain vocabulary size is reached, and that's typically 50,000 tokens. So the pro of this scheme is that you can encode everything. So you can encode Chinese characters, unknown script systems. You can encode rare words, model numbers, and binary protobuf. You can encode spaces, small and large letters, and it's more or less adequate in this combination of efficiency and vocabulary size. And now let's go through the example of what we mean by next token prediction. So we start with a certain sentence. In a shocking finding, scientists discovered A, and then we tell the model to predict what comes next. And in this case, the word heard, and then the word of, and then the token, the beginning of the word unique, and then the next token orange. So we basically have this word unicorns divided into 2 tokens, and then the next word living, and so on. So we basically keep asking the model to look at the text that was already generated to generate a new word, solving classification problem basically of predicting what that word is. So this is a multi-class classification problem with 50,000 classes. Then once the new token is generated, we basically take the one with the highest probability, we append it to the input, and then we repeat the process. So we tell the model that now look at this updated text, generate a new token, and we generate the text token by token. And here's how the architecture of the model looks like. So once again, we start with the text. We tokenize that. We add positional embeddings because in transformer sequence, the actual position information is lost. So we initialize positional embedding and just add that to the embedding of the token. Then we pass that through this causal attention mask, where the first word only attends to itself, second word can attend to itself and what came before, and so on. We pass that through several layers of the decoder with self-attention, and then we get some output. And so in this output, the shape of the output is exactly the same as the shape of the input. And basically, we do what we call the right-shifted cross-entropy. So in the original input, we had a sentence that starts with the word in, and then a bunch of words or tokens after that. In the output, we say that the word in is basically left out. So the first token is going to be connected to the word A, which is saying that we want the first token that corresponds to this word in to predict the next token A. And we connect that to cross-entropy loss. So we judge the model by how well it could come up with this word A, having the word in. Then for the second token in this sequence, we basically wanted to predict shocking. So the second one goes here. So we now have 2 words in A, and the second token can attend to both of these words, and we want it to come up with the word shocking. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements in the sequence. So the final one is not really connected to the loss because it generates something new, not really from the training data, so we cannot really judge it. And the first 9 are going to be connected with the 9 corresponding words in the original text. And we just judge that by cross-entropy loss. So each of these has predicted probabilities for every class, and we just pass that through the cross-entropy loss, knowing the true labels that actually got here. Interesting thing here is that this final token, that is the only one that is used when generating, is not really connected to anything during training. So you can think about it as something that's not really being trained. Thankfully, this is not how transformers work. So transformer actually generates all of these tokens using the same weights in the decoder, the same query key and value projectors basically, and all the other stuff that's in there. So by training this decoder here to predict the word A knowing the word in. We also train it to predict the next word for the entire sentence. Okay, now let's start reading the actual code. So we'll read the HuggingFace implementation for Transformers Inference. So first, let's talk a little bit about the installation. I don't want to show the entire process. Hopefully, it shouldn't be too hard. So this is the HuggingFace Transformers GitHub repo. You should just clone the repository and then do what we call the editable install. So they have the instructions how to do that in HuggingFace website. Here it's linked under the install the library from source. And it's just search editable install. You basically need to clone the repo, change into that, and then call pip install -e. So what that does is it installs it as a library from source, thus allowing you to change the code, to set breakpoints in the code, to debug into the functions of the Transformers library itself, and it's just more convenient to look at the models that way. So here I am in the Jupyter notebook with this repository already cloned, and this is just a sample code trying to reproduce this OpenAI vignette. So when OpenAI released this GPT-2 model, they had this paper about battle language models and their implications. This is quite a famous one because it basically showed some impressive text generation from a model like that. So here's this famous one for Unicorn, where basically the model is able to generate coherent text, quite long, quite scientifically sounding. And if it weren't about unicorns, you might have mistaken that for the actual newspaper article. So here I'm trying to do the same. To be honest, I've experimented a little bit with that. I've tried a bunch of models like GPT-2, GPT-2 Large, GPT-2 XL. I think the GPT-2 XL was supposed to be as good as the one they used in the presentation. Nevertheless, I couldn't really get to the same quality of generation. So if we read what actually happens here, so this is just repeating the initial prompt, initial confining, blah, 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 and then the actual generated text. So it says, the researchers, led by Dr. David R. Williams of the University of California, Santa Cruz, discovered the unicorns in the Andes Mountains of Peru. The area is known for its unique geology and is home to a number of rare species of animals. The researchers found the unicorns in the Andes Mountains of Peru. We're supposed to find that the unicorns were able to communicate with each other, Williams said, and so on and so forth. So one thing you can definitely notice here is that the output basically repeats itself. So it states here that the unicorns were discovered in the mountains of Peru, and then the same mountains of Peru here. Nevertheless, it looks pretty nice. So for example, here the model just came up with this scientifically sounding name, Dr. David R. Williams, and then later on refer to the same person as just Williams, which is quite what you would expect in a proper English text. So there are some artifacts. It's not ideal. Overall, it still looks quite nice. So let's look at the code. So here I'm using the Transformers library. Interestingly, this library is just called Transformers. So it's a library by HuggingFace, but it's just called Transformers, sort of saying that it's not Transformers from HuggingFace. It's not some Transformers. It is the Transformers, and everyone just sort of uses them. So HuggingFace seems to be, in the business of creating just good libraries that everyone uses. So first we import this tokenizer and GPT-2, and GPT model is called GPT LM head model, language modeling head. So we initialize the tokenizer. We pass some text into that, then we tokenize the text by calling this tokenizer encode, and then we initialize the model. And then we actually call the model.generate method. So first, let's look at the inputs, so what that is. And that is basically a list of tokens. So token ID is just a number from 0 to the cap size. I think we can get the cap size like this. Yep. So the cap size is 50,257. We can also do the following. So we can just iterate over the inputs. First, we can actually decode one token like that. Right. So the first one, 818, corresponds to just the token in. Right. So now we can just iterate over all the inputs that we have to understand like what tokens were actually generated. And we'll see, in a shocking finding, scientists discovered a herd of unique horns living in unexplored, and so on and so forth. So mostly one token corresponds to one word because it's plain English text. Then some of the words are split across two tokens. And you can see that most of the tokens starts with a space, indicating that it's either a word or beginning of a word. But then some of them don't have a space in the beginning. So this horns without a space basically means that it's a continuation of a word. Let's see what else we can get from this. I was talking a lot about potential different problems with tokenizers. So for example, does the tokenizer handle small and big letters differently? Is it able to encode Chinese characters? And you can just test that in Jupyter Notebook. So let's ask it to encode the word "the." Right, we get one token out. How about two words? Interesting. Now we have two tokens, but they are different. So probably this first one actually stands for the beginning of text as well. Right. So yeah, that's interesting. Let's try to decode. What is this first one? So it's different token that probably stands for the word "the" in the beginning of the sentence. And then notice that, yeah, let's print this one as well. Yeah, so we have token "the" without the space in the beginning. We have token "the" with a space. And then if we add more spaces, we get this special token 20, which I guess stands for space. Yep. This is interesting. So we have different combinations of space and words forming different tokens. Let's try with some Chinese. Something like this. Yep. So let's see what that is. So we can see that like one Chinese character is not encoded strictly into one token. Instead, it's encoded in two, which basically means that we treat this character as just a combination of bytes, and then just encode it as a sequence, which means that we don't waste our vocabulary on loads of these unique characters, but we are still able to represent this character as a sequence of several tokens. And it's not really printable, but I guess I don't want to do that now, but I guess you can unite them into the actual Unicode of this Chinese character. Let's go for big and small letters. And it looks like big letter and small letter do indeed have different token code. Right. Now, before going into generate method, we can actually call just the model itself. So we have our inputs, which is a tensor of tokens. And we can see we have two brackets here. So it's basically a two-dimensional tensor, which basically means this is a batch of just size 1 of sequences. So each sequence is a list of tokens, and the batch of sequences is a 2D tensor. So you can just call model on that. Model from inputs. And you get out this class called Causal LM output with cross attentions. Let's just save that to predictions and just see that the actual predictions are stored in this logits component. And we compare the shape of the output to the input. So input was 1 by 45. So our input text had 45 tokens. And now the output has 45 tokens. And basically for every token, we have this 50K prediction standing for probabilities of every token. And we can also call this argmax method for the first batch, last token, and just see what actually was supposed to be generated. So let's try to decode that. Oh, it's a start of a new sequence. Not that interesting, unfortunately. All right, now let's dig into the debugger. So first I need to put in some breakpoints. So the model here, model is a GPT-2 LM head model. I just click go to definition. Thanks to the fact that I have this repo installed with pip install -e, I can just go straight through the code. I can sort through the code. And here I'm just putting one breakpoint in the very beginning of the forward method. Then I press debug cell with the one doing the model call. And here I am. So now I take in the inputs. Let's print what that is. So yeah, it's still just a tensor of token IDs. And let's read around. So I have my inputs. I pass that through the transformer. Then I get something out of that, which basically corresponds to the transformer embedding. Then we're going to project that to actual logit predictions with LM head and self LM head. Let's see the type of that. It's just one dense layer, so pretty easy. Sometimes we'll also have the loss as part of the model. We'll look at that when we read the training code. But basically, it makes sense to calculate the loss in the model itself, considering that inputs and outputs are basically the same for language modeling. And then we return this output. And this causal cross attention is basically a class wrapping a bunch of stuff together. So most of the interesting stuff will happen inside this transformer. Let's see what it is. Type of that is GPT-2 model. So let's try to find that one. And go to the forward call of that one. And just break here. I press continue. Let's see what happens. Let me print input IDs again. Again, just the same sequence of tokens. Here we also have caching. Right now it's not really used because we just do our first prediction. But basically, once I generated the first token, I append it to my input. I don't really want to recompute all the projections, all the attentions in the previous parts of the text. I only want to recompute everything for this new one token. And that's why we have cache. But for now, it's empty. So padding is going to be needed if we actually train on a batch of samples. So we have, 64 sequences in a batch. All of them might have different size, and so we'll have to pad it with zeros before passing that into the transformer. Again, not relevant for us right now. And we have device. Pass key values is exactly this key cache, something that we've computed before. Position IDs, attention mask. Right. Attention mask. Again, it's none for now. Right. Then I have positional embedding. Let's see what this self.wpe is. So it's just a sparse embedding, and position IDs is just a vector of the actual positions, which basically means that we use trainable positional encoding. So we just learn one unique embedding for first position, second position, and so on. And then we just add positional embedding to the token projection. To be honest, we've missed the token projection. It happened somewhere above. Oh yeah, it's right here. So we had our token IDs as an input, which are just integer numbers. And then we have this self.wte. And the type of that is, again, sparse embedding. So again, we just train one unique vector for each of the 50K tokens. And that's a token embedding, and position embedding is a unique vector for every unique position. Then we just add them up. Let's go forward, 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 forward. Right. Now we actually iterate over blocks. So right now we just basically created the input to the transformer, and we are going to have a bunch of layers. And we call this layer, which is called the block. Let's see what that is. It's a GPT-2 block. So let's put a breakpoint there as well. So again, it inherits from an n.module, module, which means it's just a PyTorch layer, basically, or PyTorch network. And here, I guess, is where the most interesting stuff happens. So now hidden state is this input embedding, token embedding plus positional embedding. Let's bring the shape of that. So it's 45 by 1280. So this is like the embedding size of this GPT-2 large model. So self.ln1, I believe, is the layer norm. Yep, it's a layer norm. So we save input to residual because we will need to add that later. We perform layer norm, and then we have this self.attention. Attention is defined as this GPT-2 attention class. Let's see what that is. And that's GPT-2 attention. So that's one level deeper. That's like layer number 5 for now. But again, let's read that. GPT-2 attention, again, inherits from an n.module. module. It has forward method. This should be the most interesting one. So this is the actual decoder with the causal attention. Right. And I've just clicked continue, so I'm in this attention block now. So let's again print the state, the shape of hidden state. So it's 1, batch size 45, number of tokens in our unicorn input text, and that this one is hidden size. Then we do the query key and value projections. So again, a quick reminder of a transformer. So we have our input sequence. Then we project that sequence into 3 pretty much equal shaped vectors, but with different actual parameters for query, key, and value. And then query and key will be used. The dot product between them will create the attention weights. And then the multiplication of attention weights with the value will create the output. We also have multi-headed attention. So if we have 1280 hidden size, and let's see what's self num heads, it's 20. So we have 20 heads. We're going to divide this hidden size into 20 equal parts and basically perform 20 independent attention mechanisms. And this split heads method basically reshapes the values. So key shape is now 1 by 20 by 45 by 64. So if I multiply 20 by 64, I should get the original hidden size. Right, then we calculate the actual attention. Let's see what it is. Just bring the type of that. Okay, it's a method. Let's break there and see what happens. Okay, I have my query, key, and value. I calculate attention weights by multiplying query and key. So the shape of that is going to be for every head, 20 heads, we have 45 by 45. Basically all the pairwise combinations for every sequence element. And for now, it's not really zeroed out. So let's just print how it looks like for one head. It's just some numbers, basically. None of them are zeros. But we are going to apply attention mask next. So first we do their scaling, which is just square root, I guess. It's not cross attention. And then we have this causal mask. And this mask actually looks like a lot of numbers that look like minus infinity. And let's just see what happens to our attention weights, right? So we had them before, none of them are zeros, none of them minus infinity. And then let's print what happened to that after applying the attention weights. Right, so attention weights have dimensions of 1 by 20 by 45 by 45. Let's just focus on first element of the batch, first head, and let's see where the first element is allowed to attend. And we can see that the first element is non-zero, and the rest of them is minus infinity. So this corresponds to our first word that is only allowed to attend to itself. Then as we'll look at the second sequence, second element here. Now the first two are non-zero, and the rest are minus infinity. So the second element in the sequence is allowed to attend to the first word and to the second word, but not everything else. And then the last one basically attends to everything. Now we had this minus infinity before softmax. So after softmax, I believe that will turn to just zeros. So yeah, the first element in the attention in the first element will always be 1 because it's only attending to itself. And then for the second element, we can see where it attends to. And we have dropout. And then we multiply these attention weights by value. And that's basically the main output that we had. So this is, I would say, the most important part of the model, the decoder, the causal attention mask. So again, what happened? Typical attention is query key value. We multiply query by key to get attention weights. Then we multiply that by value. We had this special attention mask that allowed first element in sequence to attend only to itself, second element in sequence to itself and the previous one, nth element in sequence to attend to everything that was before that, but not something that was after. Right, let's just try to iterate forward. Yep. So we perform this attention, then we do the merge heads operation, which is basically just reshaping of the output. Then we have another projection, which is basically a dense layer on top, and I believe the type of that, oh, it's actually 1D convolution. Interesting. Then we have dropout, residuals, and return that. Right. So I'm back in the forward call of GPT-2 block. So I calculated my attention outputs, then another layer norm, multi-layer perceptron, residual, and this is pretty much it. Right, and I'm back to my main loop. So we've just seen example of one layer. The main difference to basically any other transformer is this causal attention mask. So let's see if anything else interesting is happening here. So let's just continue forward. Here. Yep. Then we have another layer norm. And we return. And that's the output of the entire model. So as we've seen, nothing much basically happening on top of just the model itself. Right. So let's print the shape of that. So the output of the transformer has the same shape as the input. So the basically the hidden size of that is this embedding dimension, 1280. And then I project that using just one dense layer into something that has the same shape as the vocabulary size. So I basically project these 1000-something hidden size into probabilities for every token. And this is the output. So now I should return to my Jupyter notebook. Okay, we're back in our Jupyter notebook. We've completed the model inference code. Now let's read model generation code. Again, it is going to have a lot of unnecessary details because the library itself basically works with everything, every model that came out since the original transformer. In our case, we are only interested in how it works for GPT-2, which is relatively simple. So before we even start reading the code, we can basically create a plan of what we are looking for. So we know that at some point we have an input, we're going to pass that through the model and get out the output. And then we somehow use that to generate the next token. Then we just append the token to the input and repeat the process. So let's try to read that in the code. Before I do that, I want to actually put the breakpoint somewhere in the beginning. Then again, I just click debug cell and see what happens. This generation code is located in utils.py. So it's not really part of the modeling per se, just the convenience function with this for loop that gets the output token appended to the input. So let me just quickly skim through that. I can actually tell when something interesting is happening, judging by the speed with which it executes, because it takes a few seconds to generate the prediction on my computer. Let me just validate how the actual inputs look like. So we're still looking at the 45 tokens in the input sequence. Bunch of preparations, conversions, all of that still going forward. Configurations, setting everything up. Here we have the logits processor. That might be interesting, so we'll take a look into that maybe. And now we bumped into this greedy search if condition. So in our case, we are going to do greedy search. And what that means is when the model outputs probabilities of the next token, we will always choose argmax. Advanced ChatGPT users will know that right now there's some extra options for that. For example, temperature. That's when instead of just always choosing the argmax, which is deterministic, so the model will always output the same result with the same prompt, you can go for something with randomness. So take few most likely predictions and then choose out of them based on some temperature. And so increasing the temperature will increase the randomness of the model, make it explore more rather than just sticking to the one most probable solution. So let's dig into this one. I'm going to definition and just put the breakpoint in the very beginning. And then let's iterate forward until we meet something interesting. And going forward. And now we're finally in this main loop. So it sounds as while self hasn't finished sequences, which basically, we can generate for multiple sequences in a batch at the same time. We might have some exiting condition. That's when the model decides by generating an extra end of output token that it's finished. And this is how ChatGPT basically works. So you ask it something, it keeps generating until it decides that it's enough, at which point it outputs the end of output token, and that's where the basic control gets back to you. In our case, for GPT-2, I've actually tried just generating more, and it just keeps talking and talking. So I'm guessing it's not explicitly trained to cut off the response. So it doesn't really happen. And instead just have this condition of maximum generated length. So this will basically continue until finished. Let's just validate that model inputs are still the same tokens. Yep, they are. So model inputs, input IDs. And then let's just skip through the actual model code because we've read that already. And now we are taking next token logits. So outputs.logits is predictions from the transformer, and we have predictions for 45 tokens, and then we just take the last of that as our output. So next tokens is an array that has the same dimension as vocabulary size. We have this logits processor, which turns out to be just an empty list, so we're not doing any processing after all. And then we generate the next token as just argmax. Right? And what we get from here is this end of the line token that was generated. So this is really it. We can see here that basically it continues until some stopping criteria is met. And that's it. We return the IDs. So we've discussed the inference code, the generation loop, and actually getting the token and the appending to the input stuff. Now let's discuss the training code or fine-tuning code for GPT-2. So again, we don't really know the exact training code that was used for GPT-2 because only the inference code was released. We know from the papers roughly what sort of data it was trained on. So this is the paper for GPT-1, and here they use books corpus dataset. And then in the second paper for ChatGPT-2, they also talk quite a bit more about training data. And they talk about this web text dataset. So basically they wanted to go from just books, which is about just language, and in its quite specific form of writing, quite high quality writing, which is completely different to just random stuff that you see on the internet. So an alternative to that used to be Common Crawl, which are just random pages from the internet. And it turned out that it's not really good for training because it has too much random stuff, just pages without any content or with randomly generated text and so on. So instead, they wanted to have something semi-supervised, but you can't really afford to have human labelers annotate the entire internet. And that sort of defeats the purpose, because you want to have giant data set. So what they used for approximation instead is to just scrape entire Reddit and see and look through all the outbound links with at least 3 karma. So this is like the mild supervision by Reddit users, where they say that, if it's a link somewhere and it has some karma, someone actually looked at that, it probably has something useful. And so this is the web text dataset. So it's curious that, Reddit is in the foundation of LLMs. So in this Transformers HuggingFace repository, there is a folder called examples, and then just go to PyTorch and language modeling. And they basically have some example scripts on how to run example training. So again, this is not the code that was used to train ChatGPT. It's rather a demonstration. Unfortunately, that's all we have. And so for GPT-2, we have this run CLM. So CLM stands for Causal Language Modeling. And here is an example on how to fine-tune that pre-trained model on the wiki text. So I'm going to do that straight in the debugger. And let's read that. So I have my runclm.py script here. Let's find main function. Just put a breakpoint here. And I'm just launching this file. All right, I'm in the beginning. So again, there's quite a lot of code. This is the Transformers library. It is used pretty much everywhere. So reading that again and again and again, you will eventually build up understanding on what's going on here. But for now, I just want to skip ahead to some more important concepts. So first of all, the dataset. So it is defined somewhere here, raw datasets. Let's just continue until this line, so we can actually print what is going on in the dataset. Right, so I need raw datasets and this dictionary, and I look up the dataset called train, and it's a dataset. Right, and then let's see how the first example looks like. First one is empty. Next one is some text. After that, empty again. Some more text. This looks like just a part of Wikipedia entry. Something about a Japanese, I don't know, anime character. Let's go with something further away. Yeah, again, just text. So this is the stuff that we train on. Again, this is still stuff from the internet, so it will have all sorts of weird formatting. It will have real text written by humans who didn't really spend too much time on editing. It will have a lot of different languages, potentially programming, potentially just people talking, and so on. So it's relatively challenging for a language modeling task. At the same time, as the people from OpenAI repeatedly stress in the paper, it also is wide enough to contain a lot of important tasks. So again, coming back to the paper, we can see here that they show an example of how you just naturally get this translation data set. Remember that it used to be a challenge to collect this parallel text where there's text in one language and then translation for that in another language. And here there are just organic examples where someone quotes something in French and then translate that in parentheses. And just by reading that and learning to predict what comes next, the model learns not just French, but English to French translation. And that's how it can basically pre-train and get a lot of that useful knowledge. And it happens for a lot of other tasks like programming and so on. So coming back here, we have this data set. Then before passing that through the model, we are going to tokenize it as well. And we basically wrap our data set in this tokenizer. So whatever it is that comes out of the tokenizer data set is already going to be just token IDs. Let's continue until this line and just see how it looks like. Train. First example, just a list of tokens. another example, another list of tokens, and so on. So when training the model, we'll always deal with just the text. And here we have the trainer, and the main training function is called trainer.train. Again, let's break here, continue forward, and then we call this inner train loop. So let's break here, see what happens. Nothing interesting happened so far. So we just got the data set that I've showed you, just text from Wikipedia. We tokenized that, wrapped the data set in the tokenizer. Then we have this inner training loop. We initialize data loader. Then we just go forward, until something that will look like a training loop. Right, so first note of epochs. So this is where it probably starts. Let's iterate forward. So here I am in this trainer.py line 2127. So this is where the iteration over epochs actually starts. So this one already looks at the dataset. So now inputs should already contain the specific example that we've loaded from the dataset. And then we have this training step that actually computes the loss and so on. So let's continue to that one. Right. Let's see where the model is used. So we then forward to this compute loss. Still digging deeper. Right. We are finally at the beginning of important stuff. So again, inputs, not much happened. You can judge by just how inputs have changed. So we're still looking at tokens. Now we apply the model. And remember, when we've read the inference code, we've noticed that the loss is part of the model. So let's go there and try to read it. So it was defined as GPT-2 LM head model. Let's break at the forward method, somewhere here. We call it transformer. We've read that before, so I'm just going to skip to here. Right, but now we have labels. So I had my input IDs and labels. So since we are just learning to predict what comes next in the text, labels are exactly the same as input IDs. So what I do now, I got my logits out of the model, and then I do these shifts. So LM logits are model predictions, and in this line, I'm taking everything but the last token. So let's see. Input IDs had 1024 tokens, and then this shifted logits have one less, so 123. But now for every element in the sequence, we predict 50k probabilities for every token. And for labels, we basically do the opposite. So we take everything except the first one. And then we have cross entropy loss between them. So this is what happens in the code as described in this picture. So we've got the text, we've put it through the model, we got the output out, and the output shape is the same as input shape. But now for the outputs, we take the first 2023 elements in the sequence, and we basically, when training, we're not interested in that one because we don't know how to connect it to the loss. And for labels, we take the last 2023. So we are getting rid of this first word. And then we just basically connect the model outputs to each word in the original text, shifted right. So basically, from this one sentence, in a shocking finding, site has discovered a herd of unicorns, we have like all words except the first one are used as training examples. So we're predicting in, knowing nothing. We're predicting A, knowing the first word. We're predicting shocking, knowing in A. We're predicting finding, knowing in a shocking, and so on. So it's the density of data that density of how we use the data is quite high, because we basically get a lot of signal back from every word in the input example. And this is the fine-tuning of GPT-2.